In the final video, we're going to solve another logarithmic inequality, only this time we're going to have logarithms on both sides of the equation. So as you can see in the example here, we're going to solve the natural log of 3x minus 4 is less than the natural log of x plus 6. There's two trains of thought that we can come away with and solve this logarithmic equation if you would like. And one is there's described up here, if you have the natural log of x, which is greater than the natural log of y, the only way this statement can be true is if x was greater than y. So basically you can take the arguments, if you have the same base logarithms, then you can set the arguments equal to each other. In this case, write the inequality of the arguments, and we would have to say that the x would have to be greater than or equal to y. Keep in mind, we still have to concentrate on, we never can take the log of a negative, so we got to make sure that our logarithms fit so that our argument is greater than 0, as we did in the last video that I showed you. So the other argument here that we could use and how we can solve these, and this is what we did with our equations the other day, is we can undo or inverse a natural log. So what would undo or do be the inverse of take a natural log? And that would be to exponentiate both sides to a base e. An exponential base e and a natural logarithm are inverses of each other, so you'd have 3x minus 4 is less than, same concept here, x plus 6. So we'd be looking for the answers to this linear equation. So to solve this linear equation, we're going to subtract x from 3x and get 2x. We're going to add 4 to the 6, and that means 2x has to be less than 10, which means x has to be less than 5. Now this is the beginning stages of this problem. We know that in our solution set, we want to find values of x that are less than 5. So I'm going to put an open circle there, and we want to be smaller than that. But we also have to go back to the original arguments, which are back here. Our natural log of 3x plus 4. Here's the other consideration, the detail that we have to pay attention to, that this 3x minus 4 has to be an argument that is greater than 0. It can't be equal to 0, can't be less than 0. So that means we've got to restrict our answers to values that are 3x is greater than 4 or x is greater than 4/3. So that means we can only consider answers coming from this argument that are greater than 1 1/3. So I'm going to put that relative position of 1 and 1/3. We got to make sure our numbers are bigger than 1 1/3. So right now it looks like our answers are pinned between 1 1/3 and 5. But we also have one more argument to consider. We couldn't accept any values of x for this one, this argument that would make it undefined. So we're going to take the x plus 6 and make sure it's greater than 0, which means x has to be greater than a negative 6. Well, that's down here on this part of the number line, greater than negative 6. So it would say any numbers bigger than negative 6. But we've got to go with the most restrictive one because we cannot allow to use any of these numbers here in this argument. So these are going to be discarded, not used. And we can use all of them from here to here. So with a little extra interpretation of our solution, yes, we can solve this algebraically, find our cutoff for the upper limit in this case, and the next one what we'll do is we will find from our arguments where the other limit is. So interpreting our answers, we want to take every answer that goes from, and I'm going to write it in interval notation, from 4/3 or 1 1/3 all the way up to 5, parentheses not included. And you could also write the inequality if you wanted in set Miller notation. X is an element of real numbers such that, and then you have your numbers that are between 1 1/3 or 4/3 and 5. So 4/3 is less than x, which is less than 5. So logarithmic inequalities, exponential inequalities, we can use the same basic strategies with a little extra thought process involved in here, especially with logarithms on defining your domain of both your arguments and then interpreting those for your final solutions.